Welcome to Virtual Science. I will discuss here on electrodynamics. First, start with electrostatics, then magnetostatics, and finally electrodynamics. For electrostatics, we have to deal with charge. For magnetostatics, we have to deal with magnet, and finally electrodynamics, where both electrostatics and magnetostatics are used. That means where charge and magnet are used. In electrostatics, basically charge is dealt with, and static means rest. That means in this study we will consider that all the charge are at rest, and in magnetostatics basically we deal with current. That means when when current is created, that means current is created only when charge is moved. And finally coming to electrodynamics. So let's start with electrostatics. First of all, we have to know what is charge. Charge is a physical entity, and let me start with a story. That it is well known that a hard rubber comb, when rubbed on a piece of wool, acquires the ability to attract a small piece of paper. This is due to the fact that both the rubber and wool becomes electrically charged as a result of rubbing. So now comes to charge. Charge is a physical entity, and this is like mass. It occurs when, okay, let's start with an atom. All the matters consists of atom, and atom consists of electron, proton, and neutron. Out of these elementary particles, electron, proton, and neutrons are called elementary particles. Out of these elementary particles, electron and protons are charged. Electrons are negatively charged, while protons are positively charged, and neutron has no charge. In general, a neutral atom has equal number of electron and proton. Now, if somehow the number of electron and proton is not equal, then charge is generated in the atom. Let me first consider for the positively charged atom or cation. The charge is positively when the number of proton is greater than the number of electron. As proton has positively charge and neutron has negative charge, so number of proton increases means positively charge generates, and when number of protons decreases, that means number of electrons increases compared to number of protons. I cannot eliminate a proton from the center of atom because it burns strongly. So what I can do, I can easily put an electron to the atom, or we can take an electron from the atom. And we have, if we put an electron to the atom, then atom will be negatively charged. Sorry, this will be negatively charged. This is negative, not positive charge. That means here we see that neutral, first one is neutral, second one is positively charged, having electron deficiency, and third one is the negatively charged, having electron surplus compared to the proton. Now, as the charge is measured with respect to the number of proton or electron, that is why charge is always integer multiple of the charge of electron, because only charge creates an number of atoms, number of electrons change. That means this change must be integer, not fractional. So you cannot put half electron to the atom and half electron to the outside. So either you have to put the total electron to the atom, or you have to take the total electron of the atom from the atom. That is why the charge is called quantized. Quantized means that the number of the charge is integer multiple of charge of electron or proton, whatever you can say, because charge of electron and proton are same, just oppositely. Proton is positively charged and electron is negatively charged. But this recent studies opposes this rule, the quantization rule of charge. In theoretical science, particularly in particle physics, you can study later, what a term quark. Quark is assumed to be consist of fractional charge of electron. We have talked about charge, and there is a charge, and the unit of charge is Coulomb. This is most conventional unit as well as SI unit. Now we are interested what happens if there are more than one charge. There is only one charge, either cation or anion, that means either positively charged or negatively charged, it's fine. Now if more than one charge, suppose two charges are placed at close to each other, so what happens? Actually they experiences a force. Suppose I have a charge at here, this is my a charge q1 and this is my another charge q2, and I have placed it at a distance r. So these two charges experiences a force, and the nature of the force may be attractive or repulsive depending upon the nature of the charge. Attractive force appears if two oppositely charged are placed, and repulsive force comes into play when charges are of same kind. That means either both of them are positive or both of them are negative. Now this force depends on the charge and the distance, and this was stated by Coulomb, and this is known as the famous Coulomb's law. According to Coulomb, the force experienced due to two charges placed at a distance r is directly proportional to the product of their charge. That means F is proportional to q1 and q2 independent of the sign of the charge, either positive or negative. And F is also, that means force is also proportional to 1 by r square, that means inversely proportional to the square of the distance between these two charges. I have considered here that the distance between two charges is r. So F proportional to q1 q2 by r square, and k is a proportional constant. Okay. Now interesting case arises that in we can consider only for vicinity, that means in vacuum. In vicinity, in CGS unit, k equals to 1, and in SI unit, k equals to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Permittivity of free space. And its value, the value of this one indicates 8.854 into 10 to the power minus 12. This is minus 12 SI unit. SI unit means its unit is Coulomb square Newton inverse meter to the power minus 2. So when I put this epsilon naught in this value, we can find the value of k. Okay, we have already dealt with the force between the two charges, and if they are placed at a distance, then we can easily find out the force acting on them by using Coulomb's law. Now what happens if there are more than two charges? Suppose there are a lot of charges like q1 q2 q3 and dot dot, and this is in general I can say this is charge qi. I can varies from 1 to n, and these all the charges are called source charge. And there is another charge, this is capital Q, and this is called the test charge. So we have to find out the force associated with this ensemble. If there is only one charge, suppose q1 and capital Q, then we can find easily
the force between them. Similarly, for charge q2 and q. But the most interesting factor is the force between one source charge and the test charge is completely independent of the other source charge. That means the force F1 due to charge q1 and q, that is charge q1 and q, is completely independent of the other charge. That means F1 is completely independent of F2, F3 and dot F5. And the direction of this force F1 is R1 unit vector. R1 is the distance between Q1 and Q. Now, what is the direction of R1? Suppose we have a charge Q1 and another charge Q. If both are of same kind, that means either both are positive or both are negative, then the direction of R will be towards this way. But if Q1 and Q are of opposite kind, that means either one is positive, another one is negative, then this direction is towards Q1. So the direction of R1 unit vector, or the direction of force, solely depends on the nature of two charges. Similarly, the force due to the charge q2 and q is 4 pi epsilon naught r2 square r2 unit vector, and this f2 is completely independent of the other charge. That means q1, q3 and resistance. Similarly, f3 can also be written as q3 q9, where r3 unit vector, where r3 is the distance between charge q3 and q. So the total force F is the vector sum of all the force. And that's all. Okay, this is the total force experience on the charge q, capital Q, due to all presence of all the small source charge. And this is known as the superposition principle. That means superposition principle states that the total force is the vector sum of all the force associated with it, and one force due to two charge is completely independent of the presence of other charge. Now I am interested to another one phenomena, which is called electric field. So let's check what is electric field. But before going to say what is electric field, I am considering some case. That suppose I am considering a three-dimensional case here. This is my x-axis. Sorry, this is my y-axis and this is my x-axis. There is a positive charge. Sorry, there is a charge, source charge. This is Q, and I have put a positive charge here. This is unit positive charge. Okay. Now the distance from the origin to the charge Q is R1, and the distance from distance from origin to point charge, unit point charge, is R2. Okay, this is my origin and this is R1 distance, this is R2 distance. So the distance between charge Q and unit charge, this is denoted by R, and here R will be vectorically some R1 plus R equals to R2. That means R equals to R2 minus R1. So if we have two charges at two different place and we have only the origin, so by this way we can find easily the distance. Now coming back to the point. Now I have put here a positive unit positive charge and a charge test charge Q. So the force experienced due to this charge is F equals to Q into, there is unit positive charge, that means 1 4 pi epsilon naught r square into r unit vector. From this time I will always denote the force as vector quantity. And interestingly, this is another term called electric field. So the force experienced on a unit positive charge due to a charge placed nearby is called the electric field. So electric field is nothing but a force per unit charge, and the unit of electric field equals to Newton per Coulomb, or we can write sometime as voltmeter. But Newton per Coulomb is conventional charge of unit. So electric field is nothing but a force. Okay, and what we have applied for force more than one charge, more than two charge, superposition principle, and superposition principle can also be applied for electric field case. This is this is my electric field. So the electric field due to a charge is denoted by this equation, and the direction of electric field. So there is always positive unit charge and there is a charge Q. If the charge Q is positively charged, then it will repulse the charge positive unit charge. That means the direction will be towards this way for positive charge. And for negatively charged, this is always positive and this is negative charge. This is a attractive force and the direction is towards the charge. You can consider different problem, and that's all. So as a simple case, I can consider for an example that there is a charge plus plus Q1, and there is another charge at plus Q2. Okay, these are at a distance of r, and I want to find the electric field at a point A. This is O1 point, O2 point, and the distance between O1 and O2 is r, and I want to find the electric field at A. That means I have to put a positive unit charge at A, and suppose O1A equals to O2A equals to r by 2. Okay, and now I have put a unit positive charge at position A. Now the electric field or force experienced at A due to positive charge 1 for the charge Q1 is, I am writing the electric field, this one is Q1 by 4 pi epsilon naught distance square, because the distance here is O1A, this is r by 2, and the direction is along this direction, that means along OA direction. This is unit vector, and the electric field E2 at A due to charge plus Q2 located at O2 is Q2 by 4 pi epsilon naught r by 2 square. This direction is O2 towards O2A. This will repel again. This direction will, this is O1A, O2A. As these are oppositely directed, so the net electric field sorry, because there is no enough space, I am writing it here at this position. The net electric field will be vector sum u1 plus u2, but as they are oppositely charged, they are oppositely directed, so the net field will be just subtraction of them because they are oppositely directed. You can put the value of e1 and e2 and finally get the value, and it depends on, so you can see here that the direction will be totally depends on the charge q1 and q2. If the charge q1, then there will be positive charge. If the charge q1 is less than q2, it will be greater, and as a result the direction will be another way. Now we are interested to what happens if the charge is uniformly distributed, that is for continuous case. We have we have considered so yet that the charge are discrete, that means there are these are charge, this is charge q1, charge q2, charge q3 and so on, and there is a, we have to find electric field, there is a unit positive charge, and to find the electric field we can easily find that electric field equals to sum of I qi divided by epsilon naught r square into r unit vector, because qi is the I test charge and the ri is the distance between the unit positive charge and the qth charge. So we can easily find out this electric field. Now what happens if the charge is uniformly distributed? Suppose I have a rod, this is a rod, one dimensional case of rod length L, and the charge is uniformly distributed over this length. In this case the charge is discrete charge, that means there is only one charge here and there, and in this case the charge is uniformly distributed. And for this case we have to consider the density. This is one dimensional case and the charge is distributed over the line, and this is called line charge density. And line charge density is generally denoted by lambda, and the line charge density means the charge to per unit length, charge per unit length, total charge per unit length. But if not uniformly distributed, we have to consider here a small segment of length, suppose dl, and the line charge density is lambda, so the charge for the length dl is dq equals to lambda dl, and total charge must be integrated from 0 to L. This is lambda dl equals to lambda into L. This is line charge density. Similarly, for two-dimensional case, there may be a surface charge density. Suppose this is a surface and total area of the surface is S, and the surface charge density is denoted by sigma. And if we consider an infinitesimal surface here, this is an infinitesimal surface, and the surface charge density is sigma, so the charge for this small surface ds is sigma into ds, and the total charge to be integrated sigma ds over surface, that means sigma into s. And there may be another one, this is called the volume charge density. Suppose I have a three-dimensional configuration, suppose let's say cube, let's say sphere, let's something three-dimensional case, and the charge is uniformly distributed over this volume, and in this case volume charge density arises. Volume charge density is generally denoted by rho, volume charge density. And if we consider an infinitely small volume dv over the region, then the charge due to this volume dv is dq equals to rho into dv. So total charge will be volume integration of rho dv, indicating that rho into v. This is the case of charge for continuous case. So the what will be the electric field for this case? For the discrete case, I have write down the electric field here by this equation, but for continuous case this equation can be written as q by r square r unit vector. For continuous case, I have to consider for a small for a small region first, and the charge is for dq, and then we have to integrate it for finding the total electric field. This is for continuous case. Now, for line charge density for one dimensional case, this electric field will be 1 by 4 pi epsilon naught lambda dl by r square r into vector. For two-dimensional case, that is where the surface belongs, the electric field looks like this: 1 by 4 pi epsilon naught sigma ds by r square r into vector. And for three-dimensional case, this looks like rho dv by r square into r into vector. So there may be a huge number of problems, and you have to solve these for for different continuous case and discrete case also. And I hope you will consider you will practice more problems, use more problems for your better performance, and the later will be discussed on the next class. More will be discussed in the next class. Please subscribe our channel and comment in the comment box, and for further query please mail us at farsighteach@gmail.com. Thank you.